Let's take a look at some synthesis strategies that we might use that pertain to aldehydes and ketones. Remember, when we are confronted with a synthesis problem, we want to ask two questions. What is the change in the carbon skeleton? And we learned several reactions in this chapter that allow us to change the carbon skeleton. They allow us to make a C-C bond, or break a C-C bond, perhaps. We learned the Grignard. We already knew mostly about the Grignard from the alcohol chapter and the epoxide chapter. We learned the Wittig reaction. Remember that will take a ketone or aldehyde, turn it right into an alkene. The cyanohydrin reaction adds a cyanide as a nucleophile to an aldehyde or ketone, making a new C-C bond. And on the previous video, we learned the Baeyer-Villiger reaction. And that actually breaks a C-C bond and installs an oxygen next to the carbonyl, depending on what substituents are already attached to that carbonyl. Also, the second question we ask ourselves, or actually I would say the first one, is what is the change in functional group? That's typically the first question I ask, but it really doesn't matter. We're going to basically focus on both of these questions during our analysis of a synthesis problem. So what is the change in the functional group? There's a great summary page at the end of your chapter. I will direct you to that page. But primarily we learned that aldehydes and ketones can add water, they can add alcohol, they can add amines, they can add Grignards, and that this all results in a change in functional group. We can add NaCN, as we talked about on the top of this slide. We can add a Wittig reagent, and there are many more. So I suggest that you take a look at that summary page at the end of your chapter. Let's take a look at a couple of synthetic samples now. So here's some practice. We're going to analyze these questions or these problems. The first thing that I see is that I have kind of a 6-carbon ring. I've got the same 6-carbon ring with a 1-carbon substituent that I've circled in red here. And so I need to add this amine group with an isopropyl on the nitrogen. So I think the last step will be formation of the imine from this aldehyde and this amine. And I can do this with acid catalyst, provided I make sure I'm within the pH range that imine formation is favored in. But that's going to be my final step. So then the question becomes, how do I make this aldehyde from the starting material? There's no change in carbon skeleton here. There's just a change in functional group. I have some functional group on the end of this alkene. So if I can put a functional group on the end of the alkene that I can then turn into an aldehyde, I think that would be a good strategy. And I know how to do that. I can use BH3THF followed by NaOH, H2O2, and that will put a functional group on the end carbon, which I can then play with to make the aldehyde. That's actually one step. Our good friend PCC, or the swern, should make that aldehyde, and then we can mix it with the amine to make the imine product. And that's that. That's just a 3-step sequence. The next reaction here involves a 3-carbon chain that we see right here. I'm not really sure where this 3-carbon chain ends up in my product, but maybe it's right here. And if it is right there, that gives me a hint as to what I might expect. This functional group, I hope you recognize as an acetal. It is the same as having a ketone in this position. It's just one step, one reaction to make the acetal. So if I had a ketone in this position, and I observe that I made this C-C bond sort of adjacent to the ketone, not directly attached to it, that's pretty indicative of maybe an epoxide ring opening using a Grignard nucleophile, ending up with an OH in this position, oxidizing to the ketone, and eventually making the acetal. So the acetal is made with this 1,2-diol and some acid catalyst. It's made from the ketone. That ketone can be made from an alcohol. That alcohol can come from ethyl Grignard followed by mild acid workup of that epoxide. And that epoxide comes from the product by simply oxidizing the alkene to the epoxide. So that's a simple 4-step sequence that allows us to get to this acetal. A couple other questions here. We have a alkyl bromide going to this slightly longer molecule, and I think I can observe again the starting material. It's right here. And that gives me the hint that I need to make this CC bond somehow. And there are a few ways I know how to make CC bonds. This is a single bond, so maybe it's a not a Wittig, but a Grignard. A good indication that it might be a Grignard is that I already have a bromide here, so it's very easy to turn that into a Grignard. And I know that the result of a Grignard addition to some carbonyl species is an alcohol, and I know how to make alkenes from alcohols, so that might be a good place to start. Probably if I had an alcohol here, I could make the alkene using certain steps. Let's look at the alcohol that I would get. And I'd want to eliminate to form the less substituted alkene versus the more substituted alkene. So I need to do a couple of steps here. First, I should make this into a better leaving group, tosyl chloride pyridine. We learned that reaction in first semester. That should be pyridine. And second, I want to choose a large base so that I can favor the less substituted alkene. So I'm going to use T-butoxide. So that's a little 2-step sequence to eliminate this alcohol, making the desired less substituted alkene. I can make this alcohol and this bond right here via a Grignard reaction between acetone and the Grignard. There's my Grignard, and I follow that up with mild acid workup so that I can protonate the O-, giving me that H. And then, of course, I am one step from the Grignard by just reacting my starting material with magnesium. So here I have Grignard formation, 1 step, react it with the aldehyde and mild acid workup, 2 steps, and then tosylation and elimination in a E2 Zaitsev Hoffman type product, the less substituted alkene, using the large bulky base. So this is just an E2 reaction right here in the last step. Okay, so the next step, the next reaction, appears that we start with 5 carbons and we end up with, looks like 6 carbons. So I've added a carbon. Most likely it is this carbon, and that means that I need to make this CC bond. And so you see that I start with an alcohol on this 5th carbon, or on the 1st carbon from the right. I end up with an alcohol on that same carbon if these 5 carbons are the same. So is there a way to just add a new carbon group directly to that alcohol? I don't think so. But remember that an alcohol is the equivalent to an alkyl halide, it's the equivalent to an alkene, it's the equivalent to a carbonyl species, all with just 1 step of reactions of alcohols. So I can turn this into a carbonyl maybe, and that might help me make this CC bond. And if you remember from this chapter on ketones and aldehydes, essentially being able to add a carboxylic acid as a 1-carbon group, making a new CC bond, that comes from a nitrile, a cyanide, a CN- group that we add, and then we would hydrolyze it with strong acid and lots of water. So we can do this reaction as our final step. Strong acid, water, heat. So that nitrile will hydrolyze under these strongly acidic and harsh conditions to make the carboxylic acid. And we can add that nitrile via reaction under acidic conditions with CN- and the appropriate aldehyde. And I can get that aldehyde from my starting material via PCC or the Swern oxidation. So again, we're taking our alcohol, we're oxidizing it so we can add a nucleophile to it, we're regenerating the alcohol, and then we're taking that new nucleophile and reacting it with some strong acid and water to get to the carboxylic acid. So we've added one carbon this way, and we've turned that carbon into a carboxylic acid. One more example to work on for synthesis problems in the ketone and aldehyde chapter. Let's see here. Let's look at, I have 6 carbons I count here. And I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons over here. So that's interesting. And I don't have any 6 carbons all connected to each other like I did here. It appears that I have 5 on one side and 5 on the other side. So that's also interesting. Somehow we've cleaved a carbon off of this 6 carbon chain. And if we think about ways of cleaving carbons, we've learned ozonolysis in first semester organic. And did we learn anything this chapter that will allow us to cleave carbon-carbon bonds? And we did. The Baeyer-Villiger reaction should allow us to do that, and conveniently enough, it will end up with an ester in place of a ketone. So I think the last step is probably a Baeyer-Villiger where we've installed this O. So let's redraw everything without that O. And let's put in our peroxy acid. Again, R doesn't matter because it's not around. It's not going to be around for long. And so now the Baeyer-Villiger will cleave this bond preferentially because this is a secondary carbon. This is a primary carbon. And so we get cleavage over here. We add the O on this side, and that's exactly what we get for our desired product. So I think this is definitely the final step in this reaction. Now the question becomes, how do I take this aldehyde to this 10 carbon ketone? And I need to add 4 carbons somehow. And I hope you'll recognize that this 6 carbon fragment now does appear in my intermediate. I've circled them both in blue. Those are the same 6 carbon fragment. So now I need to add essentially this 4 carbon fragment to my original aldehyde. And I can add carbon fragments to aldehydes using Grignards. And I can also get back to a ketone from that resulting product. So let's go ahead and do that. And I'll go back to red here. The appropriate Grignard is 4 carbons. Mild acid workup. Remember that the product of an aldehyde plus Grignard is a secondary alcohol. And I hope that you see that it's quite easy to take this secondary alcohol to the ketone intermediate. Again, PCC or the Swern should work just fine. You could also use H2CrO4 if you like using toxic metals. You could use Na2Cr2O7 with some acid and water. If you like using toxic metals. So any of these 4 options will work. PCC also has toxic metals, so the Swern is probably the least environmentally toxic reaction. PCC and Swern are the mildest compared to these chromic acid reactions, so I would probably suggest one of those top 2. But this is how we would analyze this seemingly diverse or very complex product, just thinking that we need to cleave a carbon because we don't have 6 in a row. We don't have these 6 in this blue dash. Those 6 don't appear together in the product. So that's our clue that we've cleaved a CC bond somewhere in here. We need to think how we cleave bonds. This is the aldehyde and ketone chapter, so chances are we learned about it in this chapter. That is the Baeyer-Villiger reaction.